Okay, good morning, students. Good morning, students. Today, let us see about intermediate code generation. Okay, so I am Dr. A.K. Jaitanvi, Assistant Professor, Department of Computer Science and Engineering, RMD Engineering College, and Autonomous Institution. Okay, first is the introduction part. In computing, code generation is the process by which a compiler's code generator converts some intermediate representation of source code into a form. Example, machine code that can be readily executed by a machine. The front end of a compiler translates a source program into an independent intermediate code. This intermediate code generation, as you all know, it plays a very major role. In the previous class, we have seen about parsers, lexical analyzer, and the phases of compiler, right? So our fourth phase of the compiler is the intermediate code generation, right? The front of the compiler translates a source program into an independent intermediate code. Then the back end of the compiler uses this intermediate code and generate the target code, right? Next. Now, let us see what is machine independent intermediate code. Because of the machine independent intermediate code, portability will be enhanced. It is easier to apply source code modification to improve the performance of the source code by optimizing the intermediate code. So we have the source code, target code, and in between is the intermediate code. So already we have seen in the previous class about these phases of compiler, right? So high level language is the input, assembly code is the output, right? The first phase is the lexical analyzer, second phase syntax analyzer, third phase semantic analyzer, then you have intermediate code generator, code optimizer, and finally is the target code. The two pillars which is required for the entire phase of compiler are symbol table and error handling. Let us see the various intermediate representation. High-level IR, high-level intermediate code representation is very close to the source language itself, not preferred for target machine optimization. Hence, it is not preferred. Then is our low-level IR, right, intermediate representation. This is very close to the target machine, and this will result in an optimized code. Okay. Now, let us see about the various commonly used intermediate code representation, right? So the various commonly used intermediate code representations are as follows, right? For postfix notation, as you all studied in your data structure subject previous semester in the last academic year, that you have three types of traversals: in order, pre-order, and post-order, right? Now here it is our postfix representation. The postfix notation for the expression a plus b is ab plus. First you will be having the operands, then you will be having the operator. No parentheses are needed in this postfix notation because the position and the number of the arguments of the operators permit only one way to decode the postfix expression. In postfix notation, the operator follows the operand. Next is our three address code. So my dear students, are you familiar with this word three address? That means we'll be having three addresses. The first address is for the operand 1, second address is for the operand 2, and the third address is for the resultant operand. So totally we need three registers, right? So three address location, three pointers, right? So hence the name three address code. It can also be said as TAC, tag. A statement involving no more than three references, 2 for operands and 2 for operands and 1 for the result, as I said. Three address statement is of the form x is equal to y opz, here xyz will have address memory location. It can be represented in three forms: quadruples, triples, and indirect triples. Next, we'll see each and every intermediate representation. The first one is the quadruple. Each instruction in the quadruples presentation is divided into 4 fields, right? It is called as operator, argument 1, argument 2, and the result. My dear students, so we saw three address code, we had three operands, right? So that is argument 1, argument 2, result. Now, why this is called as quadruple is we are storing this in a form and each and every row is pointed once again. So you have another extra field, right? So you have operator, argument 1, argument 2, and the result. So we store the operator also. Next, let us see the triples. So here it has three fields: operator, argument 1, and argument 2. Okay, so you can see the example there. A is equal to B plus C into D. So we are multiplying C into D first. So the operator is multiplication operator. C is argument 1, D is argument 2. Okay, next is B plus C. Right, what is that now? C into D, it is, the result is in 1. So we say it as B plus 1. Right, so the operator is B. The first argument is, the operator is plus, the first argument is B, and the second argument is 1. Finally, we are assigning the resultant value to A, right? So the resultant value is available in 2. The operator is equal operator, that is the assignment operator. Okay, so we should very clearly remember the difference between the assignment operator and the relational equality operator. Okay, now here in the third location, we are having the operator as equal operator, that is assignment operator, then only one argument, that is the resultant value which is stored in 2. Next, let us see about the indirect triples. Now, this representation is an enhancement over triples. It uses pointers instead of position to store the results. This enables the optimizers to freely reposition the sub-expression to produce an optimized code. Now, the another form of representation is our syntax tree. As you all know that syntax tree, it is a binary tree format where the root and the intermediate nodes are the operators and the leaves are the operands. The syntax tree is nothing more than condensed form of a parse tree. So you know that in second phase, parse tree is constructed using the context free grammar. The operator and the keyboard nodes of the parse tree are moved to their parents, and a chain of single productions is replaced by single link in syntax tree. The internal nodes are operators and the child nodes are operands. Now, this is an example for syntax tree. So, A plus B into C. First, we'll be executing A plus B because it is within the parenthesis and it has a higher precedence. So, you have plus as a root and left child as A, right child as B. Now, the resultant value of this A plus B will be available in here, the plus operator, and that we are multiplying it with C. So, your multiplication operator is the root. Thank you, students. So today, let us conclude the session by saying that in our fourth phase of the compiler, intermediate code plays major role. So 3-address code is the general format used. When you want to represent the 3-address code programmatically, right, in that case, we have three types: triples, quadruples, and indirect triples. Okay, students. So this is intermediate code representation. Thank you, students.